In this video, I am going to solve the problem 35th from chapter 19. The temperature of 3 mole of an ideal diatomic gas is increased by 20 Celsius degree without the pressure of the gas changing. The molecules in the gas rotate but do not oscillate. So here we have 4 questions. First question, how much energy is transferred to the gas as heat? Second, what is the change in the internal energy of the gas? And the third, how much work is done by the gas? And the fourth one is, by how much does the rotational kinetic energy of the gas increase? So we have to answer for these 4 questions. So let's rewrite what is given in the question first. So in this question, they gave the information about the number of mole of a diatomic gas. So here, N takes the value of 3 mole. And the gas is ideal diatomic gas, right? So it's a diatomic gas. And the most important thing here, its pressure is not changing. That means it's under constant pressure. And also they just mentioned the information about the change in temperature. So change in temperature here is 20 Celsius degree. So here we have the unit as Celsius degree. So now I have to ask you a question. Is Celsius degree is equal to degree Celsius? Is both are same? Actually it is not. The Celsius degree refers to the change in temperature, but degree Celsius is the temperature of only one body. But the unit here, either Celsius degree or Kelvin, both are same. The change in temperature in terms of Celsius and change in temperature in terms of Kelvin will give the same answer. So the Celsius degree is also same as Kelvin. So please don't add 273 here because the unit is not degree Celsius. Here the unit is Celsius degree. Clear? Okay. So now we have to answer one by one. The first question, we are going to find what should be the heat is transferred to the gas as heat. So first of all, we have to write the equation for the heat energy for constant pressure. So Q, which is equal to NCP delta T, where Cp for the diatomic gas takes the value of 7 over 2 times of R. Now I'm going to substitute this Cp here. By that, this equation will become N multiplied by 7 over 2 times R multiplied with delta T. Now I'm going to substitute the value. N takes the value of 3 multiplied by 7 multiplied by gas constant 8.314 and multiply with delta T here is 20 over 2. I got the answer for the heat. Q is equal to 1.745 multiply 10 power 3 joule. Clear? Now in the second part, we are going to find what should be the change in internal energy. What's the formula for change in internal energy? As we already studied the rule in the theory, the change in internal energy is given by the rule NCV delta T, where Cv for the diatomic gas takes the value of 5 over 2 times of R. So now I'm going to substitute this value here. By that, this equation will become N 5 over 2 multiplied by R multiply delta T. So I am going to substitute the value for each and every parameter here. So N is the number of moles, which is 3 multiplied by 5, and the gas constant is 8.314, and the change in temperature is 20 over 2. I got the answer here as 1.247 multiply 10 power 3 joules. The third question, so this is the answer for the B part. So now we have to move to the third part, work done. So in the third part, we are going to find the work done. So for this, I am going to use the first law of thermodynamics, which is Q, which is equal to the change in internal energy plus work done. So we have to rearrange this equation in terms of work done. Therefore, work done, which is equal to Q minus change in internal energy. So here Q we already found from the first part, which is 1.745 multiply 10 power 3 minus the change in internal energy value is 1.247 multiply 10 power 3. So I got the answer for the work done here as 498 joules. So this is the answer for the third part, work done. Fourth part. So here we are going to find the answer for the change in rotational kinetic energy. So how we can find the value for the change in rotational kinetic energy? So for getting this value, we have to use the rule the change in internal energy, which is equal to the change in translational kinetic energy plus change in rotational kinetic energy. So we already have the value for change in internal energy, but we have to find what should be the value for change in translational kinetic energy. So for this, we have to use the rule which we already studied in the theory. So first, what I'm going to do, I'm going to find the answer for change in translational kinetic energy. Once I found the answer for this, we are going to find the answer for the change in rotational kinetic energy. Clear? Okay. So the change in translational kinetic energy is given by the rule 3 over 2 times n or delta T. We already have the value for the number of moles, which is 3. So I'm going to substitute the value here. 3 over 2 multiplied by 3 multiplied by the gas constant value is 8.314 multiplied by the delta T is already given in the question as 20 Celsius degree. So when I just work out, so after I calculate this, I got the answer here as 748.26 joules. So this is the answer for the change in translational kinetic energy. So now I'm going to take this value and substitute the value here, as we already know the answer for the internal energy change. So I'm going to take the answer from here. So what is the answer for the change in internal energy? 1.247 multiply 10 power 3 joules. So I'm going to use this value here. So before that, I have to rearrange this equation because we are going to find the answer for this. So if you rearrange, what you will get, change in rotational kinetic energy, which is equal to change in internal energy minus a change in translational kinetic energy. So now I'm going to substitute the value, as we already know the value for the change in internal energy, which takes the value of 1.247 multiply 10 power 3 minus, and what is the value for change in translation kinetic energy? 748.26. So here I got the answer as 498.74 joules. So this is the answer for the change in rotational kinetic energy. So this is the answer for the last part. That's it. Thank you.